In this video, we're going to be looking at arithmetic with the real numbers as well as some inequalities. So for the arithmetic, I'm just going to preface that we're going to assume that all real numbers are going to satisfy the normal laws of adding, subtracting, multiplying, and dividing. And also mentioned in the previous video, we're going to assume that we cannot divide by 0. And I also want to preface that infinity is a concept and not a value, at least in this course. So we can't say that infinity is a real number. That doesn't make sense. Now let's discuss inequalities. So inequalities are going to be very useful for proving a lot of things. But I want to discuss a few mutually exclusive inequalities that we'll be using. So one, we'll say that A is greater than B. A is equal to B for 2. And for 3, A is less than B. These are mutually exclusive. So there's also ones that are not mutually exclusive. We have, A is, I'll kind of put these aside. We have A is greater than or equal to B. And, A is less than or equal to B. So when I say mutually exclusive, there is no way for any real number to be in both categories, or not both, categories 1, 2, and or 3. So, for example, if I say A is 7 and B is 3, it can only fit in either condition 1, condition 2, or condition 3. It cannot be in 2, and it definitely cannot be in 3. So which one is it? Well, A is greater than B. That's true. A is equal to B. That's not true here. 7 is not equal to 3. And A is less than B. Well, 7 is not less than 3. So this only fits for condition 1. Let's do another one. I'll choose 12 for A, and I'll let B also be 12. So which condition does this fall under? Is A greater than B? Is 12 greater than 12? No. Is A equal to B? Is 12 equal to 12? Yes. Is A less than B? Is 12 less than 12? No. 12 is 12. It's not less than 12. And what I wanted to bring up with being mutually exclusive is that if we use these over here as well, it's true that we could say, I'll call this condition 4 and condition 5. It's possible that if these are the same number, they can belong to both condition 4 and 5, right? So we can say 12 is greater than or equal to 12, or 12 is less than or equal to 12. So for the most part, we're going to want to be pretty explicit. It's just safer to use the mutually exclusive conditions. However, you will definitely see greater than or equal to or less than or equal to. And most of the time, you won't really have to worry about it, but it's just something to keep in mind. So when I say mutually exclusive, there is no overlap at all. These two over here are not mutually exclusive. There is overlap because of the equal signs. That's the only thing. So let's get rid of those examples. And really what I want to look at now is 4 statements that we're going to assume true throughout the analysis. So kind of draw a line here. We're going to assume 4 basic rules when we're working with inequalities. So using these rules, we can deduce a lot of other things. So condition 1. If A is bigger than B and B is bigger than C, then A is greater than C. Right, this is just if you are familiar with basic proofs, this would be the transitive property. I hope I remember that one correctly. I think it's called the transitive property. And if we just look at this on the number line, right? If we have a number b, a is bigger than b, so a is somewhere over here. B is bigger than C, so C has to be somewhere over here, right? So it ends up being true if we just look at A and C and their relationship. A will be bigger than C, always. So you can think of B as kind of like a mediator in between them. So that's the idea. We're not going to formally prove these. We're going to assume these are true. And here is the second condition, or the second statement. We'll be assuming true. If A is bigger than B, and C is any real number, so we can say that and C is an element of the real numbers, right? Then we can say that A plus C is bigger than B plus C. All this statement says is, assuming A, B, and C are real numbers, we can just add C, some real number C to both sides, right? So if I have A is bigger than B, I can add both sides, or I can add C to both sides. I get A plus C is bigger than B plus C. That's the assumption here. And we'll look at our third assumption. We will say if A is bigger than B, and C is positive, so we'll say and C is greater than 0, then the product AC is bigger than BC. So what does this tell us? Well, this is kind of like rule 2, right? We assume A is bigger than B, and I can multiply some number C on both sides, and recall that C is greater than 0, so that means that A times C is bigger than B times C. That's it. Now our fourth one's going to be very similar, but instead of C being positive, C is negative. So if A is greater than B, same thing, and C is less than 0, then we would actually say that A times C is less than B times C. So you probably have used this rule before throughout, in algebra when doing inequalities. If you multiply both sides of an equation by a negative scalar, when you're working with inequalities, you have to flip the sign. That's the idea. So, right, if I have A is bigger than B, but this time I multiply both sides by C, but C is a negative number, and that actually means that I have to flip the sign. So A times C is going to be less than B times C. And again, we're going to assume all these are true. So when we're doing proofs later, we can refer to these. We won't prove these explicitly, but these are kind of the way you can think about it. So that will be it just for the inequalities. So we will be referring to these rules in some future proofs. In the next few videos, I'll be doing some examples and proving them, and then I'll be looking at a few exercises as well.